Welcome back. Our next speaker is Gábor. He'll continue talking about probability on Kazhdan groups.
Thank you. So I will finally define Kazhdan groups. So I do that. So this will be my first definition of Kazhdan groups. And again, I'm just talking about discrete groups, so finitely generated countable groups. So gamma has Kazhdan's property P if for every unitary representation, representation on a Hilbert space, so rho will be the representation and gamma. So unitary transformations in a Hilbert space without fixed non-zero vectors So a fixed vector means that it's fixed by all the group elements. Rho G, V equals V for every G. That's what a fixed vector is. Okay, the Hilbert space could be real or complex. It actually doesn't matter. So without fixed non-zero vectors, there are no almost invariant vectors. So there is a positive kappa and a finite subset of the group elements, such that for every V, I guess non-zero V, if you look at, okay, sorry, for every V, there is a K in this finite subset such that the representation moves, I mean, little k moves the vector by a significant amount. Like this. Okay, that's the definition. So if you haven't seen then some digestive. So note 1. I always get wrong. I think it's correct, but I can. Okay, yeah. There is no. It's what? So if K is the empty set, then it's hard to find a K that moves. So every vector, so there is some finite yes, but that's sort of a consequence of things. Okay, there will be a note 3 somewhere, or note 4 about the. Okay, let's start digesting this because So one is what is amenable compared to this. So if I want to write amenable, that means that, okay, there's a specific unitary representation that amenability, non-amenability is talking about, which is the left regular representation. If the left regular representation, lambda, which is really the simplest representation, you just take all the square summable functions over gamma with the counting measure. That's a Hilbert space, and gamma acts on functions by translating the function. Okay, and what is amenable? Well, you have sort of these almost invariant functions, right? So for every okay, so I'm going to take I'm going to negate these quantifiers here. So for every finite k and every let's say epsilon positive, there is some function in R2 gamma and there is some k. No, sorry, such that every k in k, the translated one, so f k inverse x. I mean, so is it okay if I write it like this? So the translated function minus the original function, the R2 norm of that is less than epsilon times the R2 norm. Right? So however you take a finite number of group elements, you will find a function that is almost invariant with respect to these finitely many elements. So it's like a Föllner, well, okay. So okay. Okay, just to make sure, let me check that I still haven't messed up the quantifiers. Okay, so really, so non-amenable, so sort of this, okay, non-amenable is that the left regular action has a spectral gap in the, has a spectral gap, right? So the, so, okay, no, right? Non-amenable, sorry. So non-amenable is different in two ways from Kazhdan. So one is that it's talking only about the left regular representation, and it's talking about not about the spectral gap, but it's talking about the spectral radius, right? So there is this thing here that where is it? That Kazhdan is talking about only representations without a fixed without fixed vectors, right? And here we don't have that. So in particular, if you have an infinite group, then the left regular representation doesn't have fixed vectors at all. Sorry, I didn't want to say that. I want to say that if the group is finite, then you do have fixed vectors. The constant vector is in R2. So it cannot be non-amenable, but it still could be Kazhdan because it's not a representation without fixed vectors. Okay, so that will be note 2. That finite groups are amenable, but Kazhdan. Okay, right? Right, so they don't have a spectral. So the spectral radius is 1. They are amenable, but they do have a spectral gap for the left regular representation. And in fact, what I'm saying is that they also have a spectral gap for any representation. So maybe I prove it. Okay, so actually with right, if I want to prove that I need, so I want any unitary representation without fixed vectors, and I want a kappa and a k for any. So what I'm saying is that k equals gamma, and kappa equals square root of 2 works for any finite group. Okay, and and why is that? Well, assume that it doesn't. So assume that that these things don't work. So assume that rho k, well, okay, so k is g, k is gamma, so any gamma, any g. So assume that this minus this, right? So for so there is no so for every v there is no such k. So for every g it's less than square root of 2. Okay, and I'm going to show. So assuming this, I want to produce actually a non-zero fixed vector. Okay, so what does this mean? What is the square root 2 coming from? So we have v. So that means that the image is in the half space closer, given or closer to v. So take the hyperplane orthogonal to v in your Hilbert space, and right. So it's a unitary representation. So the length of this is the same as v's, and all the ones that this distance is exactly square root of 2 are those in this hyperplane, and those where it's less, it's somewhere here. So they are in the, if it's strictly less than square root of 2, then it's in the open half space closer to v, which means that if we average all of them, a finite group, I can just do the average. It is still in the half space. right? Average, and if this average over the group, it's obviously invariant under the action, right? Because it doesn't matter if I average this way or first I multiply every element by a certain element and then I average. Right? I'm going through the same set with the same weights. Okay, and since it's in the open half space, the average is non-zero. So it's an invariant non-zero vector. Okay. Okay, however, okay, maybe that will be node 3. But if the group is amenable and Kazhdan, then of course the left regular representation tells you that it's not Kazhdan if the representation doesn't have non-zero vectors. Therefore, for infinite amenable groups are not Kazhdan. Sorry, what? So each vector belongs to the open half space. That's a convex set. So the average is also in the open half space. Okay. Okay. Okay, maybe I put it here. Node 4. Okay, so yet another way to get confused about quantifiers is that every unitary representation has this kappa and k. So here, for instance, there was a uniform kappa, but how is it in general? So in the definition, it seems like this kappa and k can depend on the unitary representation, but in fact, there's a uniform one because if if you have if ρ1, ρ2, and so on are unitary representations with their own kappas, sorry, I don't hear.
He's asking whether all groups that you're looking at are discrete or not.
Yes, I did say that at the beginning. Yes. So there's a general, yes. So where should, yeah. So discrete. So it doesn't fit anywhere. Okay, this is not visible, but okay, fine. So finitely generated groups. Okay, so there's a more general version for topological groups. So you would just say compactly generated, and you would want to say that there is a compact. So not a finite K, but a compact K. And the rest is the same. So if we have a certain number of unitary representations, then we can always take the direct sum of the of the representations, and there is a kappa corresponding to this pi, and there's a k corresponding to this pi, and they work, this kappa and k, they work for all of the rows, right? Because you cannot, I mean, these representations are contained in there. So in particular, all the, any possible vector that causes trouble is sitting in the direct sum. So, whatever you have here works for all the individual pieces. For all the row i's as well. So if so the kappas, so there's a uniform kappa for all of them. Meaning, right? So for this representation, there is a kappa. So there is a kappa that works for any countable subset of the kappas. So there's a uniform kappa for everyone. Okay. Okay, sorry. Note 5. Okay, I'm getting confused about the notes. There are many. So, okay, so I'm not going to prove this, but that was so this definition was made by Kazhdan in '67, and his reason for doing that was so he proved that SLDR has P. Okay, of course I have to say here the general version. Okay, which implies so with DF is 3, implying that every lattice in SLDR has, okay, he proved that implies that lattices have property T, and his reason for doing this was that he proved that being Kazhdan implies that you are finitely generated. For a countable group, being Kazhdan implies that you are finitely generated. There is some, okay, it's not very hard to prove, but I'm not going to do it. So, and T, so countable T implies finitely generated. So really, he wanted to prove that lattices are finitely generated, and that's why he came up with the notion. Okay, and in fact, so not only they are finitely generated, but if you take any finite generating set, then that works as a K. So for any finite generating set, there is a kappa. Yeah. Okay. Okay, now, so I'm not going to talk about this, but okay, how to prove, so fine, this is the definition, and he proved that SLDR and some other groups are Kazhdan. How do you do that? So how do you actually produce these groups? How do you prove? So I don't really know that. I know. I mean, I have read some proofs. So for SRDR, so somehow D equals 2 doesn't work, but it is important that. But still, SL2R or SL2Z sits inside SLDZ, and some of the fact that SL2R has a pretty chaotic action on R squared helps in proving property T for the larger ones, for these extensions. The actual thing that you do is that this acts on R squared, and then you look at this group or Z, doesn't matter. And this group has relative property T relative to Z squared. Whatever, I'm not going to define it. But anyway, so the action of this on Z squared and the chaoticity of that helps. So that one sort of that's one way of doing these things. Another one, a more recent one, is by Ozawa et al. Okay, which I don't remember. So they proved that the automorphism group of the free group with D at least 5 has property T, and they did it by some calculations in the group algebra of this thing, and it's automated calculations in the group algebra. So it's a computer-assisted proof. So we realized that if certain things are true in the group algebra, then it has to be Kazhdan, and they were able to check those things. There are hyperbolic Kazhdan groups. Okay, also among these matrix groups, and okay, they can write that. So. So there are all sorts of examples, but it's not completely well understood who are the Kazhdan groups. Okay. Okay, maybe I leave the definition. So hopefully by now it's almost clear to you what Kazhdan groups have to do with expander graphs. You can sort of guess, but so this was an observation of Margulis in 73. that if you have, so if gamma is Kazhdan, and it has finite factor groups, okay, of course, okay, with the size is going to infinity, then so we take a generating set for gamma, and then look at the Cayley graph of gamma n with S, or okay, if you want to be more precise, then there is some vector map and this projection, and then look at the image of the generating set with respect to with respect to what? To the image of the generating set. So, for instance, so SF3 Z mod P. And P goes to infinity over the primes. Then these are expander graphs with it's finite bounded degree. Maybe sorry, before that I should have, okay, I guess I should have. Okay, so here I should have had a node 6. So, okay, so infinite amenable groups are not Kazhdan. There are some Kazhdan groups. How about the simplest non-amenable group? So the free group. Why is not the free group Kazhdan? So, okay, it's non-amenable. The left regular representation does have a spectral gap. I mean, okay, a spectral radius. It doesn't have fixed vectors. But how about other representations? So what is a bad representation for the free group? Well, the free group, so let's say F2 is not Kazhdan. Because, okay, so there's an obvious projection of F2 to Z. Just, if F2 is generated by the letters A and B, okay, just forget the letter B. So that's A3. Right? So this is a homomorphism, this obvious thing to Z. And this homomorphism tells you that F2 actually acts on L2 of Z. By translations, exactly the same way as Z acts on it. It's a bigger group, but it's completely not non-free action. You don't see that it's F2. It's just like Z acting on L2Z, and Z is an infinite amenable group. This doesn't have a spectral gap, so this is a bad action. So really, if a group has a non-Kazhdan factor, then it cannot be Kazhdan, because you can do the same. Whatever representation tells you that the image, the factor group is not Kazhdan, you can pull back that representation to show that the big group is not Kazhdan. Okay, but here the point is that so gamma acts on all these factor things, and because of Kazhdanity, it acts with a spectral gap. Therefore, these are expanders. That's the proof. So what did they want? Okay. Yeah. So okay. So this is not the right. If this is not the correct thing yet, because this has invariant vectors. So take this. So these are the functions with right, and okay. So S was a generating set. So this is a connected graph. Therefore, the one is a simple eigenvalue. So things that are orthogonal to the constant vectors, so that they sum to 0. This doesn't have any more invariant vectors. Right? If it's a disconnected graph, then one constant on one and the other constant on the other. This is a two-dimensional space of invariant vectors, but here we don't have that. So no invariant vectors. And then, just so do I have to say more? So right, if right, so because of Kazhdan, so I can just start writing down, but it's kind of the same as that we did yesterday. So we know that for every f in here, there is some. Okay, so in this action, so there is an element in S in this action, so we can take the projection, which acts the same way, such that right so it's not at all an invariant function. Right, and we take so this is for every f. So in particular, if we take f to be alpha times the indicator function plus beta times the indicator function of the complement, setting alpha and beta such that this is in this space. And applying this, you will find that the boundary of A already in the direction of S is big. So this, applying this to that gives you that Okay, let me write it like this. Okay, and there is some actual number, which I think, anyway, some constant times kappa squared. Okay, and A, again, it's at most, the size of A should be something at most GN half. Otherwise, the calculation doesn't work, right? So the C would be that. Okay, right? Because, so you are moving out the indicator in the direction of S. So in the edge boundary, the edges are labeled by the generators, if you want. And already in the S, already the S boundary is large. This is saying, so of course, the total boundary is even larger. Okay. So this is a way to produce expanders. Okay, so there is this other connection between Kazhdan groups and expanders that I mentioned yesterday, kind of after the talk. So let me just record it. Okay, so that's a theorem of Gábor Kun. Which is that if Gn so is the opposite direction in some sense. So right, if so when you are taking these finite factors here, then locally they look more and more like the original infinite group, right? So, and they are expanders. You can ask that, so if you have some approximation of a Kazhdan group by finite graphs in this way, that they locally look more and more like your big group, your big Cayley graph, with what kind of finite graphs can you approximate a given infinite graph? So if Gn are locally converging to a Cayley graph, a finitely generated Cayley graph of a Kazhdan group, so locally converging means that for every r, every radius r, the ball. Okay, so for every r, okay, these graphs don't have to be transitive. So the balls of radius r could look differently at different places. However, I want that from most of the vertices, they look like the ball of radius r in the Kazhdan group. So for every r, if I look at the vertices such that the ball so in Gn, the ball of radius r around V is isomorphic to the ball of radius r in a let's say Cayley graph G of a Kazhdan group. So okay, and here I just take the origin, doesn't matter because it's a transitive graph, and I want that the set of such vertices, the number of these vertices among all the vertices converges to 1 as n goes to infinity for every r. Okay. So this actually has a name. It's called Benjamin-Schramm. But so Benjamin-Schramm convergence is more general than that, you can also converge not to a transitive graph, but to a random rooted graph. So it's a random graph with a root, and you want that the distribution of these, if you take a uniform random root in your finite graph, then the distribution on the R neighborhood converges to the distribution in your rooted random graph. That would be the general one, but when the limit is a transitive graph, it's easier to say. You don't need. So even without the labels. So even just, so if you take by usually a Cayley graph, I mean an unlabeled. So first you do the Cayley graph with the labels and then you forget them. So even in that sense, it's what I'm going to write is true. So that's a weaker form of convergence. You don't have to respect the labels. If G and I are locally converging to a Cayley graph, G of a Kazhdan group, then they are essentially expanders, meaning that you can remove a vanishing proportion of the edges, vertices, because I don't want to get singletons. So there is a subset of the vertices with going to 0, such that if I remove them, so take out all these vertices with the edges incident to these vertices, has all its components expanders. So, it's so uniform. Right? I mean, so there is, if the Kazhdan constant of the group is corresponding to this generating set is kappa, then there is a constant depending on kappa and maybe on the degree, maybe only on kappa, such that by removing a vanishing proportion of the vertices, all the remaining components are these uniform expanders with that constant. Okay, of course you need this. You need to remove this thing, because if you have some sequence of expanders converging to the graph, to the transitive graph, you can just put, take some, like a piece of an n by n box connected by one vertex, but such that the volume of this little thing is vanishing, is small compared to the expander here. So this will still locally converge to your Kazhdan group, because this is negligible in the definition. But this whole thing is not an expander, because this has a very bad expansion. And so you have to remove this negligible stuff to get an expander. Or if you want, it would look like this with another expander. Not at all an expander, because if you cut it here, it's very bad. But when you remove this stuff, then you get all connected components are expanders.
The number of components go.
I don't know. That, again, you can make anything, I guess, because, you could scale this picture in whatever way you want.
What I'm asking is, like, that log n is, the worst thing that is realizable? Or?
Yeah, so everything is realizable that you want. Sorry? No, it's more complicated. They contain those, of course, but you may have to remove some other stuff. It's like, it's not like you locally you can immediately recognize the group. I don't know if it's... Okay, and so let me mention that there's the famous question of Gromov and Benji-Weiss, whether every group is Sophic, which is if you take any Cayley graph, does there exist a sequence of finite graphs converging to it in this manner? So if there is, then the group is called Sophic, and no one has seen a Sophic group yet. Yes, a non-Sophic group yet. This is important because there are many theorems that have been proved for Sophic groups. So theorems that are true for finite groups can often be generalized to be true for groups that can be approximated by finite groups or finite graphs. Okay, that's actually two different notions, but okay, so approximating by labeled finite Cayley graphs, that's stronger than approximating by graphs like this. So the fact that Kazhdan groups can be approximated only in some manner actually may help in producing non-Sophic groups. So Kuhn and Andreas Thom have a paper constructing a probability measure preserving action of a Kazhdan group that is not Sophic. That's a generalization. So that cannot be approximated by sort of finite things in a certain sense. I'm not going to talk about that, but that, for instance, is a step towards non-Sophic things. Okay. So that's it for expanders. So that was the spectral definition. Now I want also an isoperimetric definition. So this was a spectral one. It's about a spectral gap in the, it's an L2 thing. An expander, we had two definitions. One is the spectral gap, and the other one is the isoperimetric. You cannot cut it. So what is the analog of that for an infinite group? Well, you want group invariant colorings. So that's this definition is by Glasner and Weiss, 87. So for every p strictly between 0 and 1, there is an epsilon positive depending on p such that okay, so every ergodic two coloring, So let's say 0, 1 coloring. Zero, one coloring of the vertices of gamma. Sorry, so ergodic invariant random. Sorry, let me start over. So every random ergodic invariant 0, 1 coloring of gamma with okay, so I will denote the measure on colorings on my colorings with mu, and omega is the coloring. So the set of omegas such that the identity, call it E, is 1, is P, and therefore it's 0 with probably 1 minus P. Okay, which one do I do? Okay, the probability that there is a generator, so there is a neighbor of the origin such that so that its color is different from the color of the identity is at least epsilon. Okay. So what is, right? So I want a random coloring, random 0, 1 coloring. It's, of course, the coloring itself is not going to be invariant. The distribution of the coloring is invariant. The marginal for 1 is P. But and I want that so in the definition what we have is that if the marginals are bounded away from 0 and 1, then the probability of disagreeing with your with a neighbor of yours is bounded away from 0. Okay, so this is the invariant analog of being an expander. However you cut your graph into 2, the proportion of edges going between the 2 classes will be positive, will be a positive fraction of the color classes, of the sizes of the color classes. And so, of course, when P is very close to 0, this epsilon will be very close to 0, obviously, just by the union bound. If most of the vertices are zeros, then it's likely that everyone is 0 around you. But for any P, there is a uniform epsilon. Okay, that's the definition. So maybe examples. Okay, let's do example. How am I with time? 15 more? Okay. So let's do the examples. Okay, we'll see if I'm maybe I'm not. Okay, let me say in words, and then if you want to know more, I can tell you after class. So why is it equivalent to the first definition? So if you have a probability measure preserving action of your group, which is this, an ergodic PMP action, right, on the colorings, then you can produce a unitary representation from that very easily. You take L2 of the measure space, and if you had and then you do the same thing. So if you had a bad coloring, then you would have a bad function. So that's kind of the same thing as, from Fellner set, just take the indicator and you find that there is no the spectral rate, there is no spectral gap. So that's a standard one. How do you go in the other direction? So from here to there, maybe it's the other one, right? Yes, so how do you prove that? So what I said says that if it's not Kazhdan this way, then it's not Kazhdan that way. So if it's not Kazhdan this way, why it is not Kazhdan this way? So if you have some bad unitary action, how do you produce a bad coloring? So look at, okay, maybe I should write it. So catch-off proof of definition 2 to definition 1. So if you have is a unitary action with without fixed vectors and but almost invariant vectors, then so you can look at so let's look at so almost invariant vectors Vn. So these are the ones that show you that it's not Kazhdan. Then you can look at the function on the group. So let's say GH, which is just the inner product of rho G of Vn and rho H of Vn. So this has a name. I forget. So this is a positive definite. This is sort of the positive definite function associated to the representation, right, at the vector Vn. So this is a positive definite function. And if you are a probabilist, and the issue with this positive definite function is that phi n, what is it? Right? So phi n of G1 actually goes to, okay, my identity used to be E, so let's call it E. Yes, yes. So, right. So when you take the identity here, the Vn is a bad sequence because for every G, this is converging to 1. Right? Because the difference between this and that is converging to 0. So this inner product is, okay, if Vn, so let's have the norm 1. So the inner product will converge to 1. For every group element. Okay, so if you see positive definite functions and you are a probabilist, what do? Is the covariance matrix of a Gaussian field, right? So take X and G, G in gamma, centered Gaussians, centered normal. So standard deviation variance 1, centered normal Gaussians with covariance. So because they are centered, the covariance is just this, equaling this thing. Because it's a positive definite function, you have such a Gaussian field. And then this is your probability space. And what do? What is the coloring? If wherever your Gaussian is positive, it's black. Wherever it's negative, it's white. And because as n goes to infinity, the correlation goes to 1. As n goes to infinity, this coloring is getting locally constant. Right? So if you are positive, then it's the probability that your neighbors are all positive is going to 1. So in this coloring, right? So this means that this says that you cannot approximate, right? Like ergodic colorings cannot be locally constant. Or a different way of saying it. So actually, if you look at the Glasner-Weiss paper, they say that the Bauer simplex is closed or something like that. I don't know the words, but they just mean that when you take the ergodic two colorings under the weak star topology, they are closed. So you cannot by ergodic colorings, you cannot approximate the coloring, for instance, which is with probability p constant 1, with probability 1 minus p is constant 0. So, right, you cannot approximate this non-ergodic coloring by ergodic ones. Ergodic ones are not getting locally constant. There is a uniform bound keeping them. Okay, so that's the idea of the correspondence between the two. Okay, how do you? So let's start using this second definition, because in my last lecture, when I will prove that Kazhdan groups have measurable cost 1, I will use this definition. Verse 4 using definition 2. So amenable, infinite amenable are not Kazhdan. So how I want to produce locally constant ergodic two colorings on an amenable group. How do I do that? Of course, I take a Fellner sequence. Okay, and I take an IID 0, 1 coloring. Bernoulli 1/2. Okay, I'm sort of moving between gamma and G, but so okay, and then I produce a new coloring, which is simply, so let sigma x be the majority of the, so everyone has a 0 or 1 vote, and around x I look in my Fellner set, And so the Fellner set translated to X. And around me, I look at the zeros and ones and look at the majority. So if they, okay, for well-definedness, maybe I assume that the cardinality of Fn is odd, so that there are no draws in the majority vote. And so I color it to 0 if the majority is 0 and 1 if the majority is 1. Okay, why is it locally constant? So you have X and the XFN here. You have a neighbor Y. You have YFN here. What is the probability that the majority votes differ and X and Y? Well, most of the people voting in X and Y are the same, except I lost here some voters and I gained here some voters. But because it's a Fellner set, the proportion of new voters, forgotten voters and new voters is small compared to everyone. Now, in the first vote, so what is the probability that this changes the outcome of the vote? So, I would say that majority is noise stable. So if I change a tiny proportion of the votes, then it's unlikely that the result changes. So, why is that? Because if there are n, so if the size of Fn is n, so if you have n votes, then if I know that 1 has 1, then typically it wins by order root n, right? Because that's a binomial distribution. So, and when I forget a little o n of the stuff and gain a little o of n other stuff, they typically will change only by little o of root n. I mean, root of little o n things. So this square root of little o n will change the original root n only if the original root n was actually not root n, but very close to 0. So the probability that in the original, in XFN, the number of zeros was, it had to be little o root n distant from the number of ones, and that has probability little o of 1. Right? Just a central limit theorem. Okay, right. So it's unlikely that this little change changes the outcome. So for large n, you are typically, you have the same number, you have the same color as your neighbors. So this is this color, and of course this is ergodic, this coloring, right? This is a if I take a any specific, for any specific n, this is an ergodic coloring, because if I take two distance, x and y are further away, so far away from each other that the Fellner sets around them don't intersect, then sigma x is actually independent of sigma y. So it's ergodic and locally constant. I have 1 minute. Okay, why is the free group not Kazhdan? With definition 2. So proof 1, just the same thing as we did before. So take the factor map to Z, color Z, like this before, like in 1, and pull back the coloring. Right? So in the 3, so my coloring on the Z copies are almost constant. So it's a while it's black, and then, okay, maybe this wasn't the best idea. And then for a long while blue, and then, okay, so orange, blue, but large pieces typically. Okay, so in this direction, it is locally constant. And in the other direction, well, it's locally constant because I don't care about this, right? So I'm really copying in this factor map, I'm copying the same thing. So in the B direction, I have the same color, and in the A, I'm locally constant. So this is the locally constant coloring of the 3. And again, ergodic. Okay, and I will talk about this other thing tomorrow more, but you can start thinking about it. So take Bernoulli 1 minus epsilon percolation bond. Percolation on the 3. Right? So what does that mean? I keep each edge with probability 1 minus epsilon, delete it with probability epsilon. So I delete very few edges. Okay, I get a bunch of components. Many of them are infinite, many of them are finite. For each component, I flip a fair coin and color all of the vertices of the component with that color. So color each component with a fair coin, with an independent fair coin. So you have blue components and you have orange components. Okay. When epsilon is small, this is locally constant, right? The probability that, with high probability, you have all your neighbors there in your own component. So you have the same color as your neighbors with high probability if epsilon is small. So as epsilon goes to 0, this is locally constant. Why is it ergodic? Do you see? No, I'm coloring infinite things with a single coin. So there is no way I cannot. So this is not a factor of the Bernoulli shift. And it is not. So it can be proved that epsilon is big enough, bigger than 1 over √4 or something, √3. Then it's not a factor of IID. It's not. You cannot produce it from locally from IID because for the infinite components there is a single coin flip. How do you decide from what? Okay, so yeah, so it's not. Sorry. Yes, it is. It is low temperature Ising model, if you know what it is. Okay, so you can think about why it's ergodic. I will tell you tomorrow. Thank you.
Questions?
Yes. Sorry. No.
The aspect of the I don't think you guys probably won't gain anything by having this random and finite.
Yes. Yes.
So let's thank the speaker.
Thank you.